Okay, here's our string, our vibrating string experiment, and as you can probably see as we pan across the string, there are two antinodes, which means this is a half wavelength from node to node, and this is another half wavelength from node to node. So the length of the string, which is about 185 centimeters, 1.85 meters, is one wavelength, and the frequency of the vibrator is 120 pulses per second, so 120 times 1.85 is about 220 meters per second. Velocity is frequency times wavelength. So that's the answer for the velocity of the wave in the string. As we change the tension in the string, of course, the velocity will change, and we need to compare our calculations to our measurements in terms of tension. We also need to measure the linear mass density with the balance, the four beam balance, to the nearest. If you're very careful, measure it please to the nearest thousandth of a gram, because the string, the sample string that's less than a meter long, will be probably more like a third or 2 or 3/10 of a gram itself. So you want to get as much accuracy from that value as you can, because it's a critical factor in the formula. Velocity is equal to the square root of the tension in the string, which we measure here by the weight hanging down, divided by the linear mass density. So you might need to adjust the variac over there, the red variac. If things get a little too wild, you want to turn the voltage down. If things get a little too tame, you want to turn the voltage up. So right now it seems to be vibrating with pretty nice amplitude and fairly stable. So we have about 1,500 grams there, and that's 1.5 kilograms times 9.8 is about 15 newtons. So that would be the tension in the string in newtons. So let's take a look at a couple other resonance conditions for different lengths. Okay, so let's try to go to maybe 5 or 6. It gets of course, as the wavelength gets shorter, the amplitudes also get smaller, and it's a little harder to count those. So let's take a look at one kind of in the middle. And as you get good with this, and we want to go up from 2, such as this, to 9 or 10 nodes. In other words, the 10th, 9th, or 10th harmonic. So let me try to set it up for the 5th or 6th harmonic, and we'll see what that looks like. So we've set it up for the 6th harmonic. There are 6 antinodes, and the length of the string now is 3 wavelengths long. And so the amount of weight on the platform is greatly reduced. It's about 165 grams, and it's about 1/10 of what it was to get the 2nd harmonic. As you try to figure out how much weight to put on the pan, you have to realize that we have a square root deal here, and it's not a linear function. So if you want to go from 2 to 4, you don't cut the weight on the pan in half. It's quite a bit less than that. So you'll get the sense for this at some point. So let's while we've got this, and this is a pretty nice vibration here, let me get the stroboscope out and show you that this looks like a wave that's just standing there, but indeed it's a wave that's going back and forth 120 times every second. So we can't even see that because our eyes don't see that fast. So let me get the strobe and show you. I got a strobe here that flashes at various frequencies. Now let me shine it on this wave that's going by, and you can see that if I adjust it fairly carefully, that I can have it flash every time the string, which is vibrating in a sinusoidal way. You can see there's nodes, there's antinode, there's a node, there's an antinode, so forth. You can see it go by, and it freezes it in that position because it flashes faster than we can see. It flashes and lights it up so that we can see where it was every 30th of a second. Now if I change the frequency, if I double the frequency, for instance, you can see it. Oh, that's halving it. Let me double it. That I can catch it on the way over and on the way back. There it is, going over and coming back. So that's a half wavelength difference. In terms of reflection, it undergoes a 180-degree phase change when it reflects. It's on the way back, it's flipped over. And so we see we've kind of frozen it in place, and it truly is a traveling wave traveling back and forth at something like 220 meters per second, according to my rough calculation. And we can freeze it, catch it as it passes over and then passes back by increasing the frequency. It's pretty nifty, and in fact maybe even a little spooky. Okay, so that's the traveling wave. We get to see it traveling back and forth 120 times every second. Okay, so here's the standing waves in an air column Kunst tube experiment. These we cannot see, but we can hear. So we have this frequency generator here, and it's set at 1,000 hertz. I will, since there's 4 setups in the lab, and maybe up to 4 different groups will be working with this at any one time, I'll ask you to put it on a slightly different frequency, and I can show you how to do that, like 900 or 1100 or 800, 950 or whatever, so that you can tell your noise from your neighbor's noise, so that you don't get confused. So it could get a little confusing. So we'll use slightly different frequencies for everybody's setup, so that you are tuned into your frequency literally. Okay, so we have a plunger here, the knob over there, and it's sort of a piston here, and the end of the piston obviously would be a node. That's where the waves are reflected. They have to turn around and go the other way. And of course they flip over 180 degrees when they do that. This is a little speaker that's I'm going to put right up against the tube. It's going to produce the sound determined by the frequency generator here, and also the amplitude. We can make it a little louder. So I'm going to turn this on, and it will become a noisy, annoying background from now on. So we've set the frequency generator at 1 kilohertz, just because that's what it was when I turned it on, and we'll turn the gain up, amplitude up to 10 volts, peak sine wave, and so what we have here is this piston, and when the piston is locates the loudest sound, which of course is an antinode, then we're going to mark it with this one of these collars. So if we move this piston in to the loudest sound, which is obnoxiously loud, we'll mark it with the left side of that collar. And we'll do that by pulling it back and finding the next antinode, which is right about there, and the next one, and the next one more, and the last one here. So we have 3, 4, 5, 6, 7, 7 positions. Oops, sorry, 7 positions. Just trying to get this out of the way. I'm going to turn this off. So 1,000 hertz. This is a half wavelength, so this is a wavelength. So we'll measure the wavelengths, and we'll know the wavelength of the sound. We know the frequency of the sound. Frequency times wavelength is velocity, and we have the formula at the end of your handout for the velocity of sound, which is roughly, at normal room temperatures, 340 meters per second. Okay, so I'm going to measure the distance from the left of the collar to the next collar, which is, and I'm doing this very casually, 17.1 centimeters. This distance is 17.1 centimeters. This distance is 17.2 centimeters. This distance is 17.0 centimeters. This distance is 17.3 centimeters. This distance is 16.9 centimeters. So if I average those out, I'll get probably 17.1 plus or minus 0.2 centimeters. So I can calculate my maximum deviation. It's 0.2 out of 17, change that into a percent, and take an average here of 7 values, which means we could apply the standard deviation analysis to get the standard deviation rather than the maximum deviation, which would be a little bit better. And that would give us the error in my wavelength, the frequency. That's an extremely accurate apparatus, and so I can be assured that whatever frequency I've set that at, it's at that frequency plus or minus something way less than 1%. So the error here is in the measurement and the average value of the inner antinodal distance, which is a half a wavelength. So when you multiply twice that distance on the average by the frequency, you should get the velocity of sound. Wait, now 17.17 centimeters, 0.17 meters times 1,000 is 170 times 2, because there's 2 of these per wavelength, is surprisingly 340 meters per second. So just a quick calculation in my head sounds like I've got a pretty good value for the speed of sound at this temperature today of the speed of sound in air. So that's the experiment. It's kind of fun. It's actually kind of annoying after a while, but it's fun to do, and you'll get some pretty good results, I think, based on my rough calculation in my head. So, well, enjoy the noise, enjoy the experiment.